So, I am Joakim Bech, I'm principal engineer in Linaro. I've been working for Linaro for almost 5 years, and you probably know Linaro is involved in a lot of different things, but one of the things we're doing is security. So I've been the lead for a security working group since 2013 when we formed the group. I've been working with embedded devices for almost 15 years, and most of the time I've spent with security. And if you want to discuss with me, I will be here to the end of the evening, and you can also send me an email if there is something you would like to follow up. So, there are two parts today. The first part is the overview. I will introduce TrustZone for, I guess, there were some hands here that you didn't really know about it, and that was what I suspected. Why was it created, and what can you use it for? And the second part then is the pitfalls, because even though you have this new cool feature, or we shouldn't really say new, but cool feature, there are still things that could go wrong, so that's the second part here. So how did we used to do security in the past? Well, everything started out with software. We didn't have any hardwareized systems really. So we had a separate division between user space and Linux. Everything was running in software. And that's not really sufficient today. We have other use cases today where we need more security. You have seen this ring concept also, but it's the same, more or less. So the problems that we see is that the privileged domain, the kernel in this case, runs everything. And that's quite a huge code base. If you take Linux kernel, for example, millions of lines of code, and there's a lot of entrance points. So you can imagine if you would like to, for example, do a code review and certify something like this. That's really hard, and I don't think anyone has been able to do it so far. Exploits, that's not really uncommon. You can look up statistics on the internet, and you can see that the trend is unfortunately going in the wrong direction. There are more and more exploits found in Linux kernel all the time. So, hardware-assisted security, this is nothing really new. I mean, it's been around for quite a while also, and there are different ways to do it. TPMs, when you have remote at the station, you have measure boot and things like that. It's found in laptops and everything. We have smart cards, and the most common place you see smart cards is probably in your mobile phones, SIM cards. You have separate integrated circuits, like this little device here, which could be used for both symmetric and asymmetric authentication, for example. There are hardware security modules for even more robust security. And then, of course, we have TrustZone. So what's wrong with these first here? Nothing. It's other use cases. So, I mean, it depends on what you need it for. So they're perfectly fine in certain areas where you need it. But, as I said, I'm going to discuss TrustZone here. So what is TrustZone? It's hardware-based security. It's a security feature that is built into most of the ARM cores today in Class A devices. You basically have another mode in the chip that you can enable. So you run in a secure mode and a non-secure mode, and that's what we can see here. So typically when we're talking about a normal Linux environment, we see this piece. So you have your applications running and you have Linux kernel. But with TrustZone, you put another domain into the system. So you can run similar here, both user space applications and a core here also. And this is isolated from the rest of the system with a bit of the bus, so you can make it aware of peripherals and things like that also. And we have this, what we call the trust application constant here. But the interesting thing for us as TrustZone developers is that we see everything running here as non-trusted, including kernel. We don't trust the Linux kernel, so sorry, kernel developers. So, where do we find these so-called TEs, trust execution environments? Well, there aren't that many, but SoC vendors, some of the big players, they have their own implementations. There are some companies like TrustZone that have a proprietary solution, and there are a few open source ones. The one we are hosting and maintaining in Linaro is called OPT, so it's also Open Portable Trust Execution Environment. We have Google have Trusty, that's a similar thing. They use it in default AOSP setups. TLK was developed by NVIDIA. I think it's discontinued right now. I haven't really talked to the NVIDIA people for a while. And there are some more that kind of brands between open source and proprietary. So who decides how you should communicate with these trust execution environments? Well, it's mainly global platform that defines the standards here. They are the one putting together all the specifications. And there are lots of specifications, but if you're working with TrustZone, there are mainly two specifications that you're interested in. So it's the client API, which is used to which tells you how to communicate with TrustZone. And then you have the internal core API, which is the API to be used by trusted applications when they need to invoke some secure services. I will get more into details soon. And there are quite a few more specifications that are for socket APIs, secure elements, team management framework, and so on. So they are quite productive. Having that said, Google with Trusted, they don't follow global platform. So that's a bit interesting. So a big player is following this, but otherwise I think most of the other T vendors are following global platform in one or another way. Here we're going to spend a little bit more time on this image. So this is the architecture that you can see. So it's the same picture that you saw a couple of slides ago, but now it's kind of blown up in more pieces. So we have our traditional Linux environment, TrustZone environment. So in user space, we have our normal applications, the native applications that we would like to run, but usually you don't want to call the global platform APIs directly. So you typically add some kind of wrapper API in between. That's just for convenience. I mean, there's nothing really preventing you from calling that directly if you would like to. The other component we have here that we call T-supplicant. And by the way, now I'm talking about Opti, which is the TrustZone environment I'm familiar with mostly. T-supplicant is responsible for things that you can't do from secure side. So for example, if you need to store something, you don't have access usually to some flash or something on secure side. So then you leverage the T-supplicant to do that for you. So there will be some communication going back and forth here. I will show that on the next slide also. There you can see that T-supplicant is also involved in doing operations here. So, as I said, storage, but it could also be involved in networking. Then, the other big thing we have here is the T framework and the driver, and that's Linux kernel. We spent quite a lot of time to get that integrated into Linux. It took almost 2 years for us to get it merged upstream. But that is the only framework officially in Linux kernel today. So we're quite pleased that we have achieved to get it up and running there now. Then, when you enter the TrustZone side, you do that through something called a secure monitor. Basically, you initiate an SMC call. So you get an exception that you take care of on the secure side, and then you enter what we call mainly this one, T-core. This is where the engine, the operating system on the secure side, so to say. T-core lays below what I mentioned about specifications, the global platform T internal API, and this is what the different applications will see when they communicate or invoke secure services. And then down here we have different functionality that you can use to do cryptographic operations, secure storage, secure time, things like that. And of course, this is kind of the secret sauce that you have, the trusted applications. And in this image here, what you actually are doing is that you are making some kind of virtual connection between the native applications in user space to the trusted applications on the secure side. All the other stuff here, that's just some kind of communication protocol. I mean, usually people end up doing the things that differentiate up here in these two parts. All right? Everyone following along? Good. So, use cases. As I started with saying, DRM. And this is not direct rendering manager, so this is digital rights management. That's usually seen as a bad word. People can have different opinions and can get quite upset about this. I'm not defending, I'm not judging anything, I'm just a messenger here. Sure, it can be intention to lock down the system. But in general, it is about the content owner. They would like to have some kind of protection of information. It could be books, audio, video, and so on. And traditional operating systems don't fulfill the requirements from the Hollywood studios and so on. So the requirements are coming all the way from Hollywood, for example, going down to everyone and end up as us, as developers. We need to implement something here. So what you do in DRM here is that if we go back here now, you basically get an encrypted and encoded video stream here, and you will go all the way down here up to the DRM Trust application, where you will decrypt the content. It's still decoded. You send it to the hardware decoder, and then you will see it on your screen. It's a use case, but it's for sure not the only use case. Another use case that is quite common is during boot, for example. This could look quite different depending on what kind of hardware you're running, but in principle, this is how it could work. So you have some kind of ROM code starting off the device. You have some kind of software bootloader, the first one, or second, depending on what you call them. You could have the secure operating system here, the trust execution environment, which verifies bootloader and even Linux or Windows or whatever you run. So that's one use case where it could be used. We have secure firmware updates. You get some kind of message from outside. So the client sends down to Linux kernel sends the update to trust execution environment, which will verify the signature and start the upgrade procedure. User assets. So I think most of us, we are using this quite heavily today. So when you log into various sites, you use it. You have your second factor authentication like Google Authenticator and things like that. Banking, I pay my bills with the phone from time to time. When I buy stuff, AliExpress, whatever, I use my phone. And I can even track my health. And all this is kind of various degree of sensitivity here. And login credentials. If you're running an Android phone today which have TrustZone, then you're probably already using it, since there is something called Keymaster, Gatekeeper, and so on involved in this. But I think like second factor authentication, I don't think Google's Authenticator application is using anything special. It's not that sensitive information in this case, but example here, it could be. Bitcoin wallets. I have a Bitcoin wallet, but my big problem is security, so I have no money in it. So, but that I can't really do much about right now. So there are different ways that you can store Bitcoin wallets. You can do cold storage. You basically print the private key on a paper and you store it safely somewhere. That's fine. You have a password protection on your desktop machine. You start application and you just basically have to grant yourself with a password. You have Android wallets, and there has been some security issues with Android wallets. And you have hardware wallets like the one I'm showing here, this Trezor and Ledger. So everything is about storing some kind of private key. I think the hardware ones here, probably good. Cold storage, probably good. Password on desktop machine. Android wallets. I wouldn't really use Android wallets for storing, certainly if I would have a lot of money at least. So, but if I could use TrustZone, if I could choose between using TrustZone or not TrustZone, I would prefer using TrustZone in this case for my Android wallet, that's for sure. So there's a lot of people here with automotive, I guess, with Global Logic. This is not really my expertise area, to be honest, but we are seeing more and more questions about this related to TrustZone also, and it touches again applications in the infotainment system where you're using payment, for example. It could be directly using the car, the interface, or it could be that you connect your mobile phone to the car and do the payments in that case. We also have car information being produced. It could be, I've just listed 3 here, GPS coordinates, speed, emission, Volkswagen emission, ring any bells? So, but the thing that I want to get to here is that how can we prevent the car manufacturers and the owners from modifying information? We have more and more information going into the cars right now. And if there would be an accident and someone could modify the information, well, that could be quite serious in a court, for example. So try to think, if you can protect this in one or another way. We have IoT devices. That's currently a bit different if you compare it to the Cortex-A class. The Cortex-M is a bit different. And in the past, you haven't really, it's been a bit tricky to do, at least in a generic point of view, since there haven't really been a good way more than play with an NPU or use the vendor's specific security. But now ARM have just published the Trusted Firmware M specification, and you can even get access to the source code. So I believe we will see TrustZone running on M devices very soon also. And I've listed a couple of examples here, the microcontrollers in general, parking devices, sensors, gateways, Wi-Fi cameras. Wi-Fi cameras is obviously the password you want to protect. You don't want to just have that in clear text on your device. Gateways and sensors, they need to authenticate each other so they know who they're talking to. So this is also an interesting thing to have in mind. So by all these examples, I've been going through now DRM, Trusted Boot, upgrade, your mobile phone, IoT, automotive, and so on. It's the same kind of information. We have some kind of credential, some kind of password, or we need to authenticate. We need to know who are we talking to on the other end. And these are typically use cases where it could be quite useful to have TrustZone. As I said, there are other ways to do it, but think about it. You have this already integrated on your system, in your core. So if you can use it, well, at least it's better to use it, I would say, than not using it. So, but TrustZone raises the bar in general. That's what I want to say. So don't neglect and just try to do things in, like I said, in the Linux kernel, for example, because there are too many flaws. So now I've said that everything is really good with TrustZone, and now we can say how hard it is to use and the problems with it. So, memory, there are different types of memory and different ways to configure memory. So we have something that we call shared memory in a TrustZone solution, because you need to send some information to the secure side and send the data back. This is shared memory, and shared means shared. So it's not becoming magically secure just because you're running, your core is running in a secure mode for the moment. So have that in mind. As long as it's shared, anyone can really read out the memory, even though the core is running on secure side. Secure memory, that's you can configure your DDR, for example, or SRAM to a secure region, and that's typically what you would like to use in this case, if you need to do some sensitive operations that is not really visible to non-secure side. Flash, I mentioned it on the previous slide. Usually there is no flash connected directly to secure side, so we need to piggyback or use flash from normal Linux environment. To do that, you need both have encryption and integrity protection. So in our secure storage solution, we typically use ASGCM to protect it. There is one problem though, denial of service attack. Well, we're running outside our control environment, so we can't really say much about denial of service. That's an issue for sure. But the information itself is good and intact. One-time program memory, well, it could be that you need to read it, and usually there are use cases where it doesn't really matter who can use it, but quite often you would like to have some kind of control of who is writing to the memory. So the message is understand what kind of memory you use in various situations. So shared memory is shared memory. External interfaces. So this slide is about the message here. Before you deploy the product, leave me the debug options. If you have JTAG enabled everywhere, well, then you have an open door to quite a lot of things. You have sniffer logical analyzers. You can basically see exactly what packets are and how they look like and so on, and logical analyzers the same. UART, well, it's quite common that you find some pins on a PCB and you can maybe just solder a UART on it, and then suddenly you can do a lot of good stuff that you weren't supposed to do. Same with SPI and I2C. So try to think about what is open when you actually are about to send out the product. We have a bunch of registers. This applies for everything, both ARM, x86, whatever. Some of those registers are quite critical. I mean, you can unlock certain parts of the system, and that kind of goes into the previous slide, where you have the different settings, how you enable things, and so on. If you forget about things like this, it could be that it's totally open, the system, if you didn't really pay attention to the registers. So I've listed a couple of registers here related to IRQ, FIQ, debug, and so on. So the important message is read the ARM architecture reference manual if you're on ARM. If you're on x86, I guess there is something similar. But pay attention to this, because this could be critical. Crypto, that's an interesting thing. So even if you run on a secure side, you're not magically secure by everything. I mean, I can run whatever crypto I want on a secure side, but that doesn't really protect you. You still have the same kind of issues. You need to be careful because, say, the initial vector, for example, if you reuse the same key and the same initial vector, well, then you're vulnerable to this kind of two-time pad attack. So, and that could happen also if you encrypt something on secure side and return back encrypted information to non-secure side. If someone would have been able to pick up that information, well, then he can start by XORing things together, cancel out the key, and suddenly you can figure out what the plain text messages were. Encryption modes. I guess everyone has seen this famous image with the penguin if you're running the ECB mode. It's on Wikipedia. So basically, ECB is block cipher mode where every block will encrypt to the same if you use the same key and message. The other modes have some kind of connection to the previous block, so you will get different encryption depending on the key and the IV in this case. So CBC and CTR are the modes that you quite often see in this case, but there are even, I mean, depending on what kind of mode you're using, you can get into different issues. Like CBC, for example, there is something called a padding oracle attack, which when you're decrypting things, you can basically affect the different bits by XORing in a certain position, and then you can basically go the way back. And the way it works is that by XORing in different bits, you can get a padding value that matches and gives a correct answer. And by doing that all the way back, byte by byte, you can figure out the plain text. With counter mode, well, as I mentioned, you have this two-time pad attack. So you still need to think about what you're doing and have all the correct integrity protection also. Random number. That's also a really important thing. If you don't have any good source for random numbers, well, then you can't really achieve any security. That's it. So you have TRNG, you have PRNG, and you have CSPRNG. So the first one is true random number generator. And that's typically noise. You can listen to a radio chip in a phone. You can pick up all sorts of noise, basically. PRNG is what you find in the C library today. And that's good if you just want to do some kind of statistical testing. That's perfectly fine in many cases, probably not all, but in many cases. But for crypto, it's not sufficient. The PRNG it's often initialized with the same seed, so you could get the same sequence again. And if you think about what I just said about keys, IDs, you usually generate those from a random number generator. So if you generate the same number again, well, then you're in the same problem again. So what we need is this CSPRNG, which is a cryptographically secure pseudo-number random generator. And what that means is basically that based on n characters, you should never be able to figure out what n plus 1 should be. So it's totally unpredictable in this case. Then we have this one. This is tricky because how should you know about all the known attacks? I guess that's just experience. You have been working with a lot of things. You have talked to different people, seen different attacks and so on. But it could be worth to at least check about things that could be known. I mean, length extension attacks. I mentioned padding oracle. And I guess everyone with security have heard about Spectrum meltdown. So here we used the cache and speculative execution to find out security issues. Okay, so the side channel attack is an attack where you can observe things that you should not be able to observe. It could be, you can measure the power, for example, how much power is consumed at a certain point in time. And by doing that, you can draw some conclusions. You can even measure magnetic field. I mean, there's a relation between power and magnetics. So you don't even have to physically put something on a device to be able to measure things here. And these are quite powerful attacks because from software point of view, everything can look fine. If you give a piece of code to a very experienced developer saying, please read this and find some bugs, and they can't find it. It looks perfectly everything. But if you, for example, inject this kind of glitching attack and change the timing of the clock cycle, well, what happens? The CPU miscomputes something. It could crash, but it could also be that registers get another value, so you basically ignore an if case. So you can imagine, if my signature is okay, blah, blah, blah. So you can basically just skip over a verification by doing these kind of attacks. So that's the real power with this one. Another thing is that constant time comparisons and calculations. So if you see someone writing a password verification routine and they use memcompare, just start scream, because that's really bad. Memcompare is verifying byte by byte the implementation. So if you have the incorrect password, it will return quicker than it will if you have a correct password, because it needs to traverse more bytes until it figures out that this was the correct password. And that's easily measurable. You can measure it by power analysis, and you can measure it even with instructions on the CPU. So an x86, I think, is called RDTSC. On ARM, you have generic timer counters and so on. And this has been an issue, not only in the past. I mean, the issue we saw now with Spectrum meltdown is that the resolution of these instructions is so high, so you can differentiate between different things like cache accesses. So one of the mitigations they did, I think it was in WebKit, they changed it from being nanoseconds precision to a few milliseconds or something like that. Then you can't really measure the difference. We have here this, I took this here, the bell core attack. So when you're working with RSA signatures and you're doing this exponentiation here, you can speed things up by doing what's called left to right implementation. And what you do is that if you have a 0, you have 2 times a big number with ones and zeros. So if you have a 0, you just do a square operation. If you have a 1, then you do a square and a multiply, which is slower. And this is measurable. So if you figure out where this signature verification starts, you can basically just weed out the entire private key. So the message here is that constant time comparisons is quite important when you're working with signatures, passwords, and things and so on. So balance the time, so it takes the same amount of time regardless if it's good or bad. Feature creep. We quite often get asked by companies, people, oh, I have this cool feature, it would be really good to run that on the secure side. Yeah, that sounds good, but why did we create these small domains in the beginning? Well, I started the talk by saying Linux kernel was a bit too big. So you can imagine what happens if you start to put more and more stuff on the secure side. Well, we will probably need a secure side soon, another hardware or something. So one goal for us as developers, architects in this area is to try to resist and say, well, are you really sure you need all that stuff running on secure side? Can't you just extract some of the bits, just do as little as possible? So that's kind of our mantra here, that only do what's really necessary on the secure side. Don't put everything there, because then you end up in the same situation again. In some cases it's unavoidable, but the same applies. I mean, try to think how you can make it as minimal as possible, because we don't want to run everything. Typically you want to run secure services, as I said, secure storage. You need to do some encryption, signature, macking, whatever. It could be that you need to have a control of secure timer, it's quite common. It could be also some registers that is only accessible from the secure side that you would like to touch. But in general, that covers most of the use cases that you need. Online resources. There are a lot of good ideas out there if you start to Google it. Some of them are really good, but some of them are terrible. So, just a gentle advice. I mean, think twice if you read something on a forum. If you listen to someone, it's probably good to double check with another person that has been working in this area to see that does this really make sense? Does it sound good? Because it could really be a disaster if you just plainly listen to, oh, this is how you should do it, and then you just do it, and well, it turns out to be totally wrong. So this is my final slide here, the conclusions. TrustZone, it's not only about DRM, and so I know I've heard this several times saying, oh, now you're running something secure, that's just because you want to log it to your system and so on. Kind of one use case, I don't deny it, but as I said also, it could protect our valuables. If, like mentioned here, my Visa number, my credit card, again, if I have the choice, storing it plainly in a software-based system, Linux, Windows, whatever, or using some hardware-assisted environment like TrustZone, then I would prefer having it in TrustZone for sure. And one thing here also that I didn't really mention, like secure boot is also one thing that people can kind of complain about. Well, I buy my hardware, I want to do whatever it's my hardware, I want to be able to run everything, my stuff. And that sounds fine to me. But if you can unlock a device, I think that was one of the Google Chromebooks a couple of years ago, you had a real physical bolt that you could turn, which opened up the device. Well, then you could do whatever you like. But otherwise, I actually think it's quite nice to have some kind of protection, secure boot, chain of trust on my device, because that helps security with the rest of the stuff I'm doing on my device. So having the choice of having some vendor putting a secure boot on the device, and at the same time having the ability to, in a maybe inconvenient way, turn off secure boot, that's the perfect thing for me, because then I can do whatever I like if I turn this little knob, or I trust the vendor which I'm using. TrustZone, as such, mentioned, you don't really get a secure system by just turning on a magic bit somewhere. You still need to know what you're doing. So all the developers, architects, we need to dig into specifications. We need to understand our hardware, how our devices are working, how they should be configured, and so on. Crypto is hard. It's really hard. There are a lot of pitfalls in crypto. So if you have never worked with crypto, I strongly recommend you to take some courses, or at least have your code being reviewed by someone that has been working with cryptography, because yeah, it's hard, as I said. And side channel attacks, it's a nasty one, and it's showing up more and more. I think the low-hanging fruits that we still see, buffer overflows, things like that will still exist. I'm not sure if we ever will get rid of it, but I think it's better under control now. Tool chains, compilers, and so on have more features to help you find bugs like that. And I think that's why we're seeing now more and more people spending more time on complex attacks against our system, like Spectre and Meltdown. That's a quite impressive thing that they come up with here and figured out how you can dump memory from anywhere. So my final message here before the questions is that I think TrustZone generally raises the bar for security, and I think we should consider using it if we have the possibility, because there's a lot of use cases that can benefit from this. So I'm open for some questions.
Thank you, Joakim. It was a really interesting presentation, and we're ready to ask questions.
Thank you for the interesting information. And I have a following question. Is it applicable only with operating system, or can work with bare metal systems?
Good question. From what I've seen so far, it's mainly been used in systems like I explained here, with a full running operating system like Linux or Windows or something like that. But we have also seen it being mentioned in microkernels, for example, where you can run a microkernel on secure, or more or less like you were saying, like in bare metal environment. So it is possible, but you still need to think about how are you dividing things, because you still have a non-secure and a secure side. So the trick is how to partition things in that case. But as such, well, there's nothing really preventing you from running it as bare metal.
Right. I'll look at it from some right.
Using of IT system will give us security, but of course we must get efficient payment. We get a lower. We get payment for performance. Is there are recommendations, some recommendation how to avoid this payment, or make it or minimize it?
Do I understand correctly about the performance penalty that you get?
Yeah.
The question that we get here. Yeah. So I should have good numbers here, but we have a couple of half a year ago, but it's currently on hold. We have started working on a benchmark framework to get more precise figures. But it isn't that expensive as you can believe it is, because it reminds more about the syscall that you do between user space in Linux, for example, down to Linux kernel, you have all roughly the same cost when you're going to the secure side and between the trust applications. So for sure you have some kind of penalty, but it's not that bad, actually. And if we're talking about, now I'm talking about Cortex-A class, but if you're talking about Cortex-M devices now with the new TrustZone for the microcontrollers, there you don't really have any penalty because they have a total different way of working. They don't have this secure monitor thing that you need to go back and forth. You can more or less go directly between non-secure and secure side as normal function calls.
Right, one more thing. On the left.
Regarding that feature script slide, how are you deciding which feature is okay for TrustZone and which one is better left in normal mode?
Yeah, good question. For example, people have asked us to put communication protocols on the secure side. So you can directly from secure side communicate to another thing. I mean, if you have the ability in hardware to do that, well, then it's possible. But again, we think that's a bad idea because let's say you have a software or issue with the communication protocol. Well, then you have an issue on the secure side. So that's one example of things that you should probably not have running on the secure side. But there's always a challenge to how you especially work with the information going back and forth also, since like I said, we don't really trust Linux kernel side here in this case on Windows. So everything that goes in and out, if you avoid having it running on secure side, then you need to have the other problem. How do you ensure that the information is okay and no one is tampering with it as a man in the middle? And there are use cases where that could be really hard, but if you're working with signed information, then you can ensure that things are okay. But yeah, it's a good question. I would say it's case-by-case decision, but in general, try to resist.
One more question?
I have a question about shared memory space between normal world and trusted world. So what is the ways to save this area, like safety from some attack to this data in shared space from normal world?
So you mean how you actually protect it in this case? How is it up?
Yeah, what is the way to protect shared space from normal world in case here we have both access from trusted world and normal world?
Yeah, so basically when you're configuring, for example, the DDR controller, the memory protection here, you set aside some part of the memory as non-secure, some part as secure. And you can, of course, also set what kind of bits, I mean, execute, read, write, and so on. And then on secure side, when you receive the information, you basically check what kind of area does this physical pointer belong to. So you have some kind of range checks when you're entering the secure side. And if it's not the correct memory that you should look, then you can kind of just return an error message saying that you are trying to access an area which you don't, or you shouldn't be able to access. So it's a memory partition with configuration and bits, and also checking information when you're going back and forth. Did that explain your question? Okay.
And one more. Stop. Come on.
So, what kind of installation does Opti provide for the services? I mean, the case when one of services is vulnerable, and what do we do with it?
Yeah, well, that's the thing here, because we talked about isolation. Let's see here. Here we have it. So, like I said, we should think about what we're doing here versus here, but we actually have the same question here versus here. Because these guys living here, the trusted applications, they're sandboxed and living separately from each other. So if there would be a bug in our password manager, then that shouldn't affect the other trust application. And at the same time, it should absolutely not affect the core itself. So, sandboxing trust applications, and that's what I also said. I mean, by saying that this is kind of the secret sauce, that what you're doing down here, the secure services, well, that is, well, we spend a lot of time here, so that's not what I'm saying. But you typically, this is where you create your services that you invoke from a non-secure world, for example.
Okay, but somehow you communicate with those services, and if you have communication protocol, then likely some in the future you'll find bugs there. So if you manage to get a control of one of those services, is it possible to find some exploits to play with other services in the secure world?
If I would say no, then I would lie, because there's always some possibilities. There was one very skilled Google engineer a year or two ago. He managed to, on a Qualcomm device, I think it was, so Qualcomm's trust execution environment, he managed to get into the secure side by basically reverse engineering everything. And he could even get access to the hardware unique key. And that's quite fatal, because a lot of security on these devices builds that you have some kind of hardware unique key which is used to derive other keys used in the systems. By getting access to that, he basically had Pandora's box open. So for sure, I mean, like any secure system, they're never 100% secure, that's for sure. So, but you have to try to limit the damage, so to say, if there should be an exploit. And one thing here is, like I said, these things are kind of sandboxed from each other. They can't touch each other's memory, and so on. So that's the general comment here. I mean, you can spend tons of money on security, but you have to put it into account how is it needed. I mean, if you have sometimes I mention an example, for example, with IoT devices. Well, if you have a bug in a light bulb, which makes someone able to turn on and turn off your light bulbs, well, that's pretty annoying. And that could, yeah, it's annoying, I would say. But what if someone could get into the same light bulb, brick the device, so it doesn't work anymore. You can't even reboot it. You can't even get into firmware upgrade mode. Well, the company behind this light bulb, they probably have a hard time in the future to convince people that we are doing the good things. So you have to put into balance, well, how much is this service worth for us to protect? And you should have a little bit more protection than it's worth. I mean, if it costs $1 million to get access to something that is worth $10 US, well, no one would do it. That's it. But if you, on the other hand, could just buy a cheap J-type debugger, get access to a shared key, for example, affecting all devices in this area, well, cheap device, I win. I have the golden key now. Well, then you should probably spend a little bit more time thinking about security.
So one last question. Do you know some Opti commercial deployments? That's the first one. And the second one, do you know some exploits for Opti?
We have no problems. If you go to GitHub on the Opti page, there is Opti_OS. You will see a link to platforms supported. I think there are roughly 25, 30 devices supported today. It's ranging from Atmel, HiSilicon, Renesas, TI devices, Breadcrumb, ARM devices, Raspberry Pi. Yeah, there's quite a few of them. Some of these are working with, or actually many of the devices that you can see support upstream are some kind of development devices. And the reason for that is that the SoC vendors who are using Opti otherwise, they're usually doing it for new products. So they are not really, they don't want to publish anything right off. I mean, they're waiting until it's kind of been released and been out for a while and so on. But there are quite a lot of different vendors using it today. And just by looking at this platform supporter, you get some kind of indication about it. There is one, it's a small company, but they have a lot of customers called Security Labs. If you go to their page, you can see the Opti logs where they're demoing when they're running a solution. Related to bugs, should I say this here? So, let me step here. This one. This was actually a bug in Opti a year ago or something. We had this implementation here when we were doing these Montgomery operations in the code. And we had to fix it, of course. Actually, it was already, the interesting story here is that it was already fixed upstream in the crypto library, the libtomcrypt that we used, but we hadn't rebased the library for a while. So we were lagging behind. So that's another lesson. Try to look into and follow the latest updates. But then we also changed this operation now, so it's another way of doing it. So you can still have quite good performance, but you can do it. But if you want to see more about it, go to opti.org. In one of the drop-down menus, you have a security advisory page. There we have listed them, and I think there are like four issues that we had now since we published it 2014. So it's not that bad. There are quite a lot of them. For Spectre and Meltdown, we have done fixes also. Since that affects the secure side also, you have the same kind of ways that things could go wrong on the secure side. So between trust applications and the secure core, you could have the Meltdown issue. So we did the same kind of mitigation as they did in Linux kernel, this kernel page table isolation. So we only keep the necessary things mapped in kernel, and yeah, that takes care of Meltdown in that case.
All right.
Yeah,
unfortunately, we are limited on time, and all other questions you can ask personally after this speak. It was a really structured way to deliver the message, and it was really easy to understand what you mean. And thank you for this. Let's